In all the previous lectures, we mainly talk about the information processing in the quantum domain, such as the quantum computing and the quantum cryptography. In today's lecture, um, to understand the quantum information better, then we also need to understand how does the classical information processing works. And then one of the popular example people are referring to when people discuss about the quantum computing and the quantum cryptography is the something called as RSA protocol. So or yeah, RSA algorithm. So in today's lecture, I will first introduce how does the RSA algorithm works. And then the main reason people are referring to the RSA is twofold. The first is why are we interested in factoring large numbers? And then the reason is because the security of the RSA is guaranteed by the difficulty of factoring a large number. And then if you click this link, then you will even see a challenge which asks the people to find out um, uh, large number of um, which will ask people to factor a large number. And then the another reason is that another reason RSA is also frequently referred in the quantum information area is that because the RSA becomes vulnerable to the quantum computing, then what will be the alternative for the security system? And then that's why we started to also discuss about the quantum key distribution system. So, however, the RSA is still useful compared to this QKD system because sometimes it can be used for the authentication. So yeah, today I'm going to introduce the RSA. So when we are discussing about the RSA encryption or decryption, we first start with a very large two prime numbers, and then in this case, and then in this example, I intentionally chose the p as the one of the prime number as 3 and another prime number as 5. And then if we multiply these two, then we will obtain this value n. So n is obtained by just p times q. And then and of course, this 15 is very easy to factor. But if these two numbers, these two prime numbers are very large, then it will be very difficult to find out factors. So that's the advantage of the RSA algorithm. And then in this case, the RSA algorithm based on this number generate two types of key. One is called as a public key and another is called as a private key. And then the public key is generated by combining this n value, which was 15, and another randomly chosen value. Yeah, even though this is 3, and then you might consider that this was the one of the factor of the 15. That's not the case. This just happened to be 3, and then you can choose any other arbitrary value for here. And then based on the combination of these two values, you can I will show you how you can generate the private key later. And then once you have these pair of public key and then private key, then you can start to consider transmitting some kind of message. And then you know that any kind of message will be represented by the binary number, or they will be encoded in the digital domain, and then all the digitally encoded value will be represented, can be considered as the binary number. And then in other words, we can also consider any arbitrary message m as the if we read such kind of value as the if if we consider any message which is represented by the binary digit as some kind of decimal number, then you can always claim that any kind of message will be represented by some number, some decimal number or whatever number. And then in this case, let's say that what Alice wants to transmit to Bob, the message Alice wants to transmit to Bob is represented as number 13. Then how can Alice transmit the information message 13 securely to the Bob? And then now the protocol starts. So what Bob does first is he first generate his own public key and then private key. And then as I mentioned, I will show you how you can generate the private key. But you know that how Bob can generate this 15, just randomly choose two very big prime numbers and then just multiply them, and then this number is just randomly chosen. And then um, Bob will keep this private key. Yeah, so if Bob loses or if Bob expose this private key to other people, then the entire scheme won't work, and then the entire scheme will just fail. So Bob should keep this private key extremely carefully. However, he for the public key, he actually announces the public key on a open internet. So anybody, not only the Alice, can see this public key. Then how can Alice transmit her secret information? Yeah, again, yeah, let's assume that the message Alice wants to transmit can be represented as number 13. Then what Alice does is she multiplies this message 13 three times, meaning so in other words, she calculates 13 to the third, and then this 3 comes from one of this public key, and then the number 15 is used as a divisor when she is calculating the modulo value. Or yeah, so what she does is she calculates this value and divide by 15, and then obtain the remainder, which is 7. And what she transmit is only 7. So and then nobody so even if any eavesdropper tried to catch this message, but the eavesdropper cannot understand what was the original value, because as you can see here, 7 seems to have nothing to do with 13. And then, however, once Bob received this encrypted message, then what Bob does is use this private key. And then the way he uses the private key is by um, calculating the power of this received message, which was 7, and then calculate the 7 to the 11th, and then what he does is he also he also divide this entire value by this n value, which is 15, and then obtained only the remainder. And then eventually, as you can see here, Bob actually recover the original message. And then this is how does the RSA key RSA encryption and decryption works. And then for the entire situation, 13 is not special. Yes, this is some kind of random. If you try any other randomly chosen number for m, yeah, if you go through this entire process, you will always obtain the you will always recover the original value by going through this one. And then this relation can be proven mathematically. And then I will do the most of the proof in the next page. And then still, yeah, one of the concept you should get is that yeah, what Alice transmit here is she calculates the m to the m to the eth, and then calculate the modulus of the n, and then once Bob receives this entire value, what Bob does is calculate the power of the power of d value, which is the part given here, and then here again calculate the mode n again. However, even though here I said that but what Bob does is he first get the only the remainder and then calculate the power of the remainder to the d. However, this will be and then and calculate the modulus, calculate the remainder again. However, this is equivalent to just calculating everything. So instead of doing the instead of calculating the remainder in the middle, without calculating the remainder, what he can also do, what you can do is you just calculate the m to the e and then calculate the power of this one, which is typically the same as this one. And then once you calculate this value, this power first, and then if you obtain this value, then this kind of calculation is the equivalent to the value obtained by this process, this procedure. So it doesn't matter whether you first calculate the mode in the middle, or you just delay the calculation of the remainder, and then you just keep the you just continue the calculation of the this power value, and then finally if you obtain this value. So whichever order you do, you will always left with the original value of m. So that's the power of the RSA, encryption and decryption. And before I explain the mathematics behind the RSA, let me give you some example of the RSA, which is typically used in our daily life. If you ever use the server, Linux server, or typically more typically Unix server, then one of the program you are using is frequently used. The program is called as something called as SSH, or some kind of terminal software. And then in that case, when you use the SSH program, you might have seen this kind of alert. And then what it says is that it is showing here. I intentionally erase some part of the public key, which is received from the server. But what server does is server will provide you the public key, and then what this warning sign shows is that your computer connected to this server computer for the first time, and then the host computer provided you the provided the public key to your computer. And then because one of the possibilities is that the hacker might be controlling the entire network, or the connection in the network, and then the hacker might provide you some different public key instead of the true public key. So and then your computer cannot actually determine whether the received public key is authentic or not. So in that case, what you have to do is ask your server administrator whether the fingerprint, and then and in this security terminology, people call this received public key as the fingerprint. And then you should make sure that the received fingerprint is authentic. And then only when you can confirm that the newly received fingerprint is correct, then you should just accept that that newly received fingerprint, and then or the public key. And occasionally you might also get this kind of warning message. And then what this says is that typically the server will reuse the same public key over and over because they're generating a new public key also takes a lot of time. So people prefer to reuse those the same public key. However, and then yeah, you might and your local computer will also save the received fingerprint in the past, and then when your local computer try to connect to the server again, then your local computer might realize that um, the received fingerprint print is different from what you received in the past. And then in that case, the scenario is two things. One possibility is that there is a really eavesdropper or the hacker in the middle, and then the hacker might be trying to act like the hacker is the authentic server. And then and another possibility is that the administrator of the server decided that the previous public key is reused too many times, and then to avoid the security to enhance the security, the administrator of the server might renew uh, the the public key. So yeah, in that case, you should actually, when you receive this kind of warning, then you might, it is better, I actually recommend that you should contact your administrator of your server, and then make sure that the newly received fingerprint for the RSA key is authentic. Now let's get back to the mathematics of the RSA key generation. So as I mentioned, the RSA key generations first start with selecting two large prime numbers, and then yeah, these we of course um, because this this prime number will be very large, and then yeah, it will be randomly chosen. So people, yeah, there is no reason or there is no way you can just guess what these two prime numbers will be. And then once you selected these two numbers, then what you will do is calculate the product of these two numbers, and then the next thing we do is we calculate this value, which is this phi of n, and it is called as the Euler's quotient function, and then this phi n is obtained by calculating p minus 1 times q minus 1. And then in this case, if we use this example, then of course this will be p minus 1, which is 3 minus 1, 2 times 4, which will be 8. And then once we obtain this phi of phi of n, or in other words, Euler's quotient, Euler's totient function, then we try to randomly select another small odd integer, but then make sure that this number is relative prime to this phi of n, which means that there is no common factor between these two numbers. So it won't be too difficult because you can always quickly check whether these two values have the common common divisor or not. And then once you obtain this value, then the next thing you calculate is the multiplicative inverse of this value with in terms when you are calculating the modulo of phi of n. So what I mean is that of course, if you just multiply d to the e, which was 3, then you will obtain 33. But if you consider the product of these two values in terms of the mode of this value, which was mode 8, then you know that this will turn into 1. And then as long as this new value of d can satisfy this relation, meaning that the result of a product of these two value becomes 1, and then this d value is called as the inverse of E. And once you obtain these values, then the public key is made by combining this E value with this N. And then the private key is also formed by combining this D value with N. Yeah, so these are the pairs. And then once you obtain those values, then what you can do is now, yeah, and then you know that this public key will be announced in public, and then this private key will be kept in secret. And then once the Alice receives this public key, then she also choose the message to transmit. And then the only requirement for the message is that the length of the bit length of the message M should be less than the length of the bit required to represent the product of this N, product N. And then once you decided the message M, then what you do is you calculate the power of M to the E, and then calculate the only obtain the remainder with respect to N, and then this value will be transmitted over the open network. And then once the Bob receives this value, then he also calculate the power of this value to the D, and then obtain the remainder with respect to N. Then if Bob calculate this value, then he is supposed to recover the value M. And then why is that the case? If you look at the calculation in this case, then what you do is once you receive this value, then you calculate the power of the entire value, and then calculate the mode N. But as I mentioned, such kind of calculation is equivalent to just calculating the power of this. First calculate this value, and then calculate the power of this value to the D, and then eventually, and then and finally you calculate the mode N, and then that calculation can be also, and such kind of calculation can be expressed in this way. And then now the product of this E times D can be replaced by this expression, because when we found out this value, we made sure that this value D is the multiplicative inverse of E with respect to modulo phi of N. And then what that means is that if we calculate the D times E mod phi of N is 1, and then this can be also re-expressed as this corresponds to some integer multiple of the phi of N plus 1. So you just replace this one with this one. So yeah, you obtain this case. And now, yeah, this can be split into the product of these two, and then yeah, and now, yeah, if you look at the theorem A 4.9 in the textbook, then there is proof that if you calculate the power of this message to the Euler's totient function, and then calculate the mode N, then the value will be always become 1. So the this factor actually does not do anything. So what you will eventually end up with is only M mode of N, and then because this n is larger than m, so eventually this value will be m, and that's how you can prove that the entire RSA encryption and decryption works for any arbitrary m. Now, let me change the topic. Yeah, so another topic you might also frequently hear in the newspaper is something called as QRNG. And then if you saw this kind of news article, which was and then now even nowadays you might hear something like one of the Samsung Galaxy phone's name is Galaxy Quantum, and then you might wonder what kind of quantum technology was involved or is included in those smartphones. And then the technology which is used in those quantum Galaxy phone is called as Galaxy Quantum Phone, is QRNG. And then all these news article is basically talking about the QRNG technology. Compared to the QRNG technology, another type of the news article which was related to a quantum computer was called was the about the new type of the cryptography system, and then this was the PQC, which was the acronym for the post-quantum cryptography. So we already discussed about the PQC in the quantum key distribution lecture. So I hope that at least once you read this article, you should be able to tell what these news articles are talking about. So what is the quantum random number generator? And then the basic idea is very simple. What we do is use the quantum superposition property to generate the true random number. And then I will show you why we call this one as a true. And then the idea, the simplest implementation is that if you just start with the polarization, which is the superposition of H and V, and then if you measure such kind of polarization using the HV basis, then you know that with the 50% of probability, this photon will be either transmitted or reflected, and then the choice between these two are completely random. Nobody determines how, at least within the frame of the quantum mechanics. Yeah, we can tell. We cannot tell, for each photon which path this photon will take. So yeah, it is completely random. And then and if we call this one as 0 and this one as 1, then the general this kind of device will continue to generate completely random bit between 0 and 1, 0 and 1. And then that's why it is called as quantum random number generator, and then the acronym is just QRNG. And then the first thing I want to emphasize is this equivalent to quantum key distribution, or QKD, or the more generally the quantum cryptography? And the answer is no. It has nothing to do with the QKD. And then that's the point I really want to emphasize, because in the news article which I just showed you in the previous page, yeah, it might sound like the QKD system or quantum cryptography system is included in the smartphone, and then that's not the case. That all it does is it is using the QRNG. Then what is the relation between the QRNG and the QKD? The only connection between the QRNG and the QKD is that if you remember the BB84 protocol, which was the simplest QKD protocol, and then in that case, what Alice should do is she should first decide what kind of value she will transmit for each of the time slot, and then for each of the time slots, she should also determine what kind of polarization basis she will use between the the HV basis or TA basis, and then in that case, um, she need a completely random number, and also when Bob receives a single photon transmitted by the Alice, then he should also decide what kind of basis he will use between the HV basis and then the TA basis, and then for such kind of decision, QRNG might be helpful, but except that it is not the QKD. Yeah, make sure that you don't get confused between the QRNG and the QKD. And then as I mentioned, yeah, we call this QRNG as a true random number generator. Then what's the difference? And then the typical random number generator you are using on the computer is called as a pseudo random number generator, because all those random number which is generated by the which is typically used in the computer is generated by very complex calculation. And then if you ever use the random function in the programming, and then you generally use those functions with the rand with some number here, and then the number we place here is generally called as a random seed number. And then because all those random number generation is done by going through very complex calculation. So if we use the same seed number, then you will always, even though the pattern of the generated number might completely look random, it is completely predictable as long as you know about the seed number. So with the classical computer, the biggest challenge with the random number generation is how we can generate the completely random seed number. And then one of the simple method is by using some non-repeating process. For example, if we use the current time, then whenever we call the function, then the number you will call the function will be quite random. So by using the current time as a seed number is a good choice. Another types of random number generation is that sometimes your computer will ask you to move your mouse like this one, and then if you keep moving the mouse, then the pattern of this movement will be completely random, and then based on the movement result, yeah, computer can generate some random number. However, these methods are unfortunately not completely random, because in somehow, yeah, you can guess when the function will be called, or the movement of the mouse cannot be completely random, because it will be limited to some kind of area. And then um, if you can guess the how this movement will look like, then somehow these numbers can be easily guessed. And then in in about 10 years ago, you probably heard about the Snowden, who exposed the fact that the um, NSA in the U.S. government were collecting the secret from many countries illegally. And then at that time, people were wondering how the NSA could collect those secret information. And then many of the security experts assumes that or guess that probably NSA was using the guess was have a good way to guess the seed number for the pseudo random number generator. And then the question is, how can we make our system secure against such kind of attack? And then the answer is, if we have a perfect random number generator, not based on this pseudo random number generator, then it might be safer. And then that's so that the QRNG will be used for such kind of purpose. Another popular application of the QRNG is for the authentication. And then the uh, authentication means that when you have some two people, two party, and then assume that they share their password. They have the same password, and then the question is, then at least want to do some kind of communication with the Bob, then Alice need to identify her own identification to Bob, and then it is called as authentication. The problem here is we don't want to send the password over the network because yeah, even though you are using some protocol, a secure protocol like SSH, but if you keep sending out the same password over and over, then there is more chance that the eavesdropper can guess your password. If you if you watch the movie called as Imitation Game, and then in that case, the way Alan Turing figured out the password of the German's army is that because the uh, German army were using the same kind of message over and over, and then based on that, such a kind of pattern, Alan Turing could figure out how to how to find out um, um, the secret message. So yeah, again, the challenge is we don't want to um, send out the password over and over. Then how can we solve such kind of problem with the random number generator? The way it works is we first generate some random number, and then we create the encrypted message, but the main message is based on this random number, and then the shared password is only used as the encryption key. So the message is mainly about this number, and then the information about the password is barely included in this message. And then once Bob received this encrypted message, then the Bob can because Bob also shares the same password, and then he can use the this shared password to recover this message. So if Bob can recover the same value, then um, and then how can Alice confirm that Bob actually correctly recovered this number? Well, the one way is ask Bob to generate a new number based on this recovery number. And then the simple example might be that just ask Bob to increase this value by 1. Then if Bob correctly recover this value, then he can also generate the correct new value. And then what Bob does is send this new value and to Alice, but now yeah, he uses the same shared password to encrypt this value, and then this new encrypted message won't have any resemblance to the original message because if the encryption method is ideal, then even if we have only one bit is changed, the encrypted message should be completely look completely random compared to this original message. And then once Alice receives this message, then because she still shares the same password, then she can decrypt the received value, and then she can confirm that Bob could correctly recover this original value. Because if Bob failed, or some some hacker who behaves like a Bob claim that he or she recovered the this received value, but then the hacker, because hacker does not know this shared password, the hacker will incorrectly recover the number, and then the whatever the hacker does, the receive the received message won't be the same as this one, and then the Alice can immediately detect that the Bob is not the authentic Bob. So and then she can just ignore the communication here. And then if there was no problem in the communication or decryption by the Bob, then what Alice and Bob can do is use this new message as a new password. So whenever the and then yeah, once the authentication is over, then what Alice and Bob will do is the actual exchange of the data, and then during such kind of data exchange, Alice and Bob will use this new number as a password, and then once the session is over, then they will discard this new number, and then by doing that, they won't they will not reuse the same password over and over, and then that will enhance the security of the previous in the security of the existing security system. So if I summarize what I just showed you, then such kind of protocol is called as a challenge and response protocol. And then what Alice does is Alice generates a random number and then encrypts the random number with the shared password and then send that encrypted message. And then Bob decrypts the encrypted message using the same shared password. And then Bob calculates a new value based on the recovered random number, and then once Bob sends back the new value encrypted again using the same password, then Alice should be able to decrypt the returned message and then verify whether Bob has the same password. Then how can we implement such kind of QRNG chip? Um, Actually, one of the reasons I'm explaining the how it can be implemented physically is because there are actually two Korean companies who are manufacturing this kind of chip, and then these are two types of case each of the companies are using. So, but before we discuss how this works, let me just get back to this kind of situation. In the previous explanation, I assume that the polarization of this photon is tilted by 45 degree, and then it is the different either horizontal or vertical polarization will be split by this um, polarization beam splitter. However, we can also use something called as 50-50 beam splitter, and then what this means is that it when we have single photon coming in, then with the 50% of chance it will reflect, and then another 50% of chance the photon will be transmitted, and then it can be considered as a partial mirror. So you probably saw some kind of mirror which will be partially reflecting the image and then partially transmitting, and then yeah, so this is exactly such kind of mirror. And then in this case, yeah, even though yeah, you might consider that this photon is just representing single um, quantum state, but if we observe that it will be eventually being split into two paths, then we can also express the quantum state of this photon as a yeah, if I write this one as the transmitted case, and then this case as a reflected case, then we can also say that the quantum state of this photon can be expressed as the square root 1 over square root of 2 and transmitted plus and then reflected. And then the reason and then every all the phenomena related to this beam splitter can be explained in terms of the quantum mechanics. And if we extend this idea, then yeah, we might consider using LED or the laser light, and then inside the yeah, if if you consider any of the laser pinpointer, then you know that inside the laser pinpointer or laser, there will be so many number of photons. However, I also mentioned that if we attenuate such kind of light beam, then we can reduce the density, and then eventually we can even reduce down to the level of single photon, on average, one photon per second or something like that. So let's assume that we attenuated the output of the LED, and then um, we shine the output of the LED on this kind of image sensor, and then image sensor will have a lot of two-dimensional pixels, and then in principle, if even if we have some kind of laser light, then the and then if we assume that we are measuring the number of photons per unit time, then the typical um, quantum state of the such kind of laser light can be expressed as the summation of the one photon and the zero photon, or one photon and or two photon, and so forth, something like this. And then depending on the type of the laser, depending on the type of the light, yeah, whether it is a laser light or the LED light or sunlight, what becomes difference is the coefficient in front of these terms. Yeah, so except that these values are different, they are all they can all be considered as the superposition. Yeah, of course, if we have a summer light, then it cannot be just expressed in this simple pure state, um, which you will which I will explain the meaning of the pure state in the next lecture. But point is, in principle, um, whether we per unit time, whether we will have a single photon or no photon or three photon, is determined by the superposition of these all possibility. Moreover, if we shine this kind of light on this kind of two-dimensional array, then you can consider this situation as the extension of this kind of beam splitter. And then in that case, if I label each of these pixels as the first pixel, yeah, we are like, if I say that the first pixel as A and the second pixel as B, third pixel as C, and so forth, then the quantum state of the entire light being shined on the this image sensor can be considered as the superposition of all these possibility with different labels, like A. Yeah, so even for the A pixel, yeah, it can be it can be considered as the um, zero number of photon um, impinging on the A pixel, and then one number of photon impinging on the one A pixel, and then two on the A pixel, and so forth. And then there will be different amount of superposition in front of that, and then um, and so these are the summation of the A case, and then there will be also other case like um, zero photon on the big pixel, and then one photon on the big pixel, and so forth. So there will be a lot of them, and then so forth. So C and D and so forth. So what we really measure is the number impinging on each of these pixels, and then the number of the measured photons can be considered as the um, is measured by the superposition of these possibilities. And then you yeah, in the current technology, people are using something called a CMOS image sensor, and then this image sensor is what is being used in your smartphone. So in the past, these CMOS image sensors sensitivity is poor, or on the other hand, you might say that it was too noisy, so you cannot really distinguish between the 1 photon and 3 photon impinging on the each pixel. But nowadays, the noise level of this image sensor became really low. So in principle, you can be able to tell whether there was 3 photon or 4 photon or 0 photon and so forth. Yeah, of course, still there is some limitation in terms of the resolution, but the resolution has been improved a lot. So that was the one way to implement the QRNG chip. And another types of QRNG chip are using the radioactive decay, like this one. So you are familiar with the concept that many of the unstable isotope of the of some atom, then they will decay over the time. And then the typical shape of the decay curve looks like this kind of exponential curve. And then what this means is that if you have 10 of or hundred of some kind of material, then each of the atom has probability of decaying at each of the different times. So even for the single atom, it might decay at this time, and then let me call this as a T1, or another time as T2, and another time as T3, and so forth. So and then the point is, we actually don't know when exactly the some specific atom will be decayed, or the nucleus of such kind of um, atom will decay. And then in principle, we can write the quantum state of such kind of atom as, or the nucleus as the T1 decay case, and a T2 decay case, and a T3 decay case, and so forth. And then of course the coefficient in front of these will be different values, but this kind of decay process can be also considered as a superposition of many different possibility. And then once we measure the time, then yeah, we might assign the value like 000, oops, or 001 and 010 and so forth. And then even if we are measuring the timing, then they can be considered as a random number. And then the source of the randomness of this process is comes from the quantum mechanics. So we can call it as a quantum random number generator. So these are the quite interesting implementation. But one of the things I actually want to emphasize here is it has nothing to do with quantum cryptography. Yeah, again, we are in to implement the quantum cryptography system. QRNG chip is might be used, actually being used a lot, but that doesn't necessarily mean the QRNG chip by itself is the quantum cryptography. And then the all the explanation I gave you, or the protocol I showed you in the previous page, is how we can use the QRNG chip to enhance the security of the classical communication system. And then again, this is not the quantum cryptography, so don't get confused when you read the article about the QRNG chip. Another topic I want to discuss in today's lecture is about the models of the computation. And then many of you are familiar with the concept of the Turing machine, but let me just give you an overview of what the Turing machine means. So a Turing machine means that this is some kind of ideal or abstract mathematical model of the computer. And then of course the modern computer does not work in this way, but this is the one proposal from the Alan Turing, who was the main theme of the imitation game movie again. And then what he proposed is the following. So when he considered the computer, then the computer will be composed of these four components. The first component is that it will have some kind of finite state, and then the state of this finite machine will be will move between several of these states, and then each of the state will be labeled as q from q1 to qm, and then there will be also starting state and then halting state, meaning the stopping case. And then there will be also a tape, and then this tape will contain each of the square in the tape will contain one symbol drawn from some set of alphabet. And then in this case, we are assuming that the alphabet gamma, the set of alphabet gamma is composed of this symbol, which indicates the left edge of the tape. And then like this way, we might have zero alphabet, or the one alphabet, and yeah, there might be more alphabet type. But let's assume that this tape can only contain either starting point, or a zero or one, and then all the others are blank. And then I will just use the B to represent the blank. So this is the alphabet, and then the only types of alphabet which can be um, written on this tape is out of these four possibility. And finally, there is a read-write tape head, and then this head can read the value at the point where the head is residing, and then based on the value read from this head, read by this head, and then the current finite state, and then a combination of these read value and the current state will be compared with the program. And then based on the instruction of the program, this head might move. This head might move either left or right, or just stop there. So that's the um, concept of the Turing machine. And I guess it still is not clear for some of you who are not familiar with the concept of the Turing machine. So let me give you some example of such kind of Turing machine. So the program for the Turing machine is generally expressed as this kind of form. And then each of the term here means that the first term, or the first term here, means the current state, current finite state. And then this second term means the value just read by the read-write head. And then the third term, or third component, means the next finite state, the machine will be changed. And then this value will be the new value, which will be updated at the head position. And the last value means that whether head will move to the right or to the left. So let me give you some more concrete example. So let's say that we started with this kind of a tape, and then this is the yeah, this is the program which I showed you in the slide. And then let's assume that our the finite state at the beginning will be q sub start, and then the head will also start from the left of the tape. Then once then at this point, then the state of the finite state is the q sub s, and then only the first line of the program corresponds to this one. And then at the same time, the head read this starting symbol. So what it should do is, yeah, so these were, so the Q sub S is red, and then also this starting point is red, and then the next thing it should do is now we have to update the state to the Q sub 1. So this value will be changed to the 1, Q sub 1, and also the this square in the first the the square under the head should be updated with this symbol, but it is already here, so it is not being erased, but it will just yeah, leave it as it is. And then finally, the head should move to the right. Plus one means the move the head to the right. So this will be moved to like this one, like here, and then the and this situation can be also represented by the finite state diagram. So in this case, we started with the Q sub start, and then um, what the first line of the program says is the at the Q sub s, if the read the value read by the head is this starting symbol, then we will just leave the same symbol at the same at that square, and then we will move to the plus one sign. And then in this case, the new state will become Q sub 1. So this is called as a finite state machine. And what happens next is that the um, yeah, now yeah, with the current state of Q sub 1, and then the head read the 0, and then this corresponds to the second line here. So Q1 and the 0, and in this case what it does is the quantum the sorry the state of the machine will still remain as a Q sub 1, but the the value in the tape will be updated to the blank, which means that this value will be simply erased, and then finally the head should move to the right, like this one. So yeah, they should be erased like this, and then what just the yeah the this second line can be also represented in this way. So if our input is 0, then it will be replaced by blank, and then it will move to 1 to the right. And the next situation is that the state is still Q sub 1, but the value read by the head is 1. So this corresponds to the third line of the program. And what we have to do is keep the state to the Q sub 1, but the value will be erased by replaced by blank. And then we should move the head to the right, which means that this value will be erased, and then the head will move to the right, like here, and then this can be also um, um, represented in this way. So if we read the 1, then it will leave the blank here, and then yeah, the head will move to the right, to the right. And again, now the current state is Q sub 1, and then the value read is 0, which corresponds to the second line again. And then in this case, the state will be the same, but the value in the uh, tape will be replaced by blank, and then the head should be moved to the right, like this one. And finally, the Q1 state, and then the value of 1 corresponds to third line, and then the Q1 will still remain as a Q sub 1, and then the value in the tape will become blank, and then the head will move to the right, which means the here, and then like this one. And now what happens is the state is still Q1, but the value read by the head is now blank. So that corresponds to the fourth line here. And now the state will be updated to Q2, Q sub 2. And then the value here will be still blank. And then now the head will be moved to the left. So yeah, this is what happens. And then now what we learned is that from the first line of the program, what we should do is blank input and then blank output, and then move to the left, and then the final state will be updated to will be changed to Q2. And now with the Q2, the value is blank. So in this case, it corresponds to fifth line. And what it does is the state won't be still state will stay as a Q sub 2, but and then the value will be still blank, and the head will move to the left. And so that means that if I read the blank, and then blank will be will remain, and then the head will move to the left, and it will continue to move to the left and move to the left, and finally it will arrive here. And then I can just erase all of this, and then now the situation is that the finite state is Q sub 2, but the value read by the head is the starting point, which means the sixth line. And then now the finite state should be updated to Q sub 3. And then the value in the blank in the tape should be the same as the before delta this starting symbol. And then now the head should be moved to the right. So something like this one. So what happens is now the Q2 will move to the Q3. And in this case, what we read is this starting, and then the same symbol will remain, and then the head will move to the right. And finally, what happens is at the state of Q sub 3, it reads the blank here, and then the finite state will be updated to Q sub halt. And then the value here will be updated to the 1, and then it won't move to anywhere else. So this can be also shown in this way. And then what we do is, if we read the blank, and then the value will be updated to 1, and then the head won't move to anywhere else. So this is the finite state machine diagram, and then this is exactly what happens. And then if you just followed all those programs, then you will realize that whatever value was written in the tape, it will eventually all erased by these two lines. And then once everything is erased, then because of these two lines, the head will move back to the original left starting point. And then once it reaches to the left edge of the tape, then it will move back to the right once, and then it will write down as a 1. So somehow this program is similar to the function of f of x, and then so you might consider the original value written in the tape can be considered as the input parameter, and then the output value will be always 1. So whatever value we have, it always generate the output value of 1. So this is the meaning of this finite state program. Now, you might wonder why we do care about this kind of machine, because this machine just looks very inefficient compared to the modern computer. And surprisingly enough, all the existing computer, it can be actually um, um, can be considered as this kind of Turing machine, or yeah, in other words, any kind of modern computer can be simulated by this Turing machine. So the meaning of the Turing machine is that um, if we, yeah, again, if we want to calculate, if we want some kind of mathematical model of the modern computer, then the job, uh, anything which can be done by uh, any kind of task which can be achieved by the modern computer can be also achieved by this Turing machine. So yeah, so this sounds very abstract, but if we want to decide whether some kind of calculation is doable or not, can be determined whether such kind of job can be implemented by or can be calculated by this Turing machine. One of the long-standing unsolved problem or a challenge in the computer science is called as a Church-Turing thesis. And then what this claim means is that um, let's say that you can think of yeah, you might come up with some kind of new computational model, and then there is some algorithm running on that computer model. Then what this thesis claim is that those problems can always be simulated or computed by the Turing machine, which I just showed you. And then, yeah, this is called a thesis because this was not proven yet. And then, yeah, one of the coverage which this thesis did not consider is about the efficiency. And then when we are talking about the computational efficiency, then what we consider is the size of the problem. So if you have to factor some very big number, and then that big number can be represented by n bit, then how much time do you need to factor that problem? And then, yeah, so not only the factoring problem, but any kind of computation problem, then to classify the problem, uh, the difficulty of the problem or efficiency of the algorithm, we use the big O notation. And then if some algorithm such as the binary search, in that case, let's say that you have some number of 2 to the n numbers, and then and then we are just assuming that these numbers are already sorted. In that case, and then if you have some x number, and then you are trying to figure out, so there are 2 to the n number, and then what you want to do is find out the closest number. You want to find out some number which is closest to the x, and then if these data are already sorted, then yeah, one of the fastest way to find out the closest number is using the binary search. And the binary search just works in the following: you first divide the entire data by half, and then compare the size of this x with the number around here. And then if it is less, then it will, yeah, you will just cut one more time, and then compare whether which side it should belong to, and then keep dividing by half. And then by doing that, um, then you can actually find out the closest number at on the order of the some number, or in the and then, yeah, depending on the algorithm, sometimes it might take n to the p, and then in this case p is some constant number. However, if all the data are not sorted at all, so if it is unsorted, in that case, there is no way you can find out the closest number within this order of the time. And then in that case, you will your algorithm will take a order of 2 to the n time. And then if your algorithm works in this kind of speed, then you call that such kind of problem as the um, p problem, because it can be solved within the polynomial time. However, if the problem cannot be solved within this problem, or you will take order of the exponential or even longer than exponential time, then they are called as the NP problem. And then all these problem belongs to something called as P space. And the definition of the P space is that the set of all decision problem that can be solved by a Turing machine using a polynomial amount of space, not the time. Yeah, so that's the definition of the P space. So within this P space, there are problems which can be solved by within the polynomial time or non-polynomial time. However, um, it is not completely clear whether there is really, and then yeah, there are a lot of problems which we believe or which seems to be non-polynomial problem, but unfortunately, there is no way you can actually prove that those algorithms are the best, and then there is no improvement you can make. So one of the fundamental question in the computer science is whether um, there is non-polynomial problem which cannot be solved at the polynomial time at all. And then even within this non-polynomial time, there are some problems or some problems which are type of the MP problems. But once you know the solution of the some A problem, and then when you are trying to solve the B problem, then even though the problem by itself are not, by themselves are not the same, but the basic algorithm, the basic idea to solve A and the B are the same. And then yeah, there is also other problem which can be also solved with the same similar approach. And then these somehow form some kind of class, and then we call such kind of class as MP complete. And then the characteristic of the MP complete problem is once you know how to solve this problem, then you can solve all the other problems. And then the fundamental question in the quantum computing is where does the quantum computing um, class exist? One possibility is a quantum computer might be able to solve the P problem only efficiently. Efficiently means that these problems can be also solved at the within the polynomial time. However, then there is no point we are interested in the quantum computer. So yeah, what people hope or what people believe is that there will be some amount of some kind of problem which does not belong to which cannot be solved within the polynomial time on the classical computer, but those problems might be solved by the quantum computer with at the level of the polynomial time. So the one of the fundamental questions we still need to figure out or prove is that there is non-negligible amount of problem which does not belong to the P problem. However, one of the still annoying part is that we still even don't know whether there is additional MP problems which does not belong to P problems. And then yeah, so yeah, proving the this relation is still not obvious, but as we are trying to prove, as we are working on the proof for this kind of um, relation, then yeah, we can also learn um, a lot of things in the computer science. Anyway, so as I mentioned before, the Church-Turing thesis actually did not consider the efficiency. So the extended Church-Turing thesis, or something called as complexity theoretic Church-Turing thesis, in this thesis, they actually consider the efficiency. And then how can we, and then in this thesis, what this thesis says is that the probabilistic Turing machine, and then I should define what probabilistic Turing machine is. And then if you remember about the Turing machine, then I showed you that the programs are generally described as the starting the current state, and then input, and then the next state, and the new value, and how should the head move, like plus or minus one, and something like this one. And then this was the kind of a deterministic program. However, the probabilistic Turing machine allows you that even if you have the same condition, then the output or the resulting state, and then the value which will be updated in the tape is not determined. It is not um, completely determined, but sometimes these with some amount of probability, sometimes it might go to Q1, but sometimes it might go to Q2, and so forth. And such kind of Turing machine is called as a probabilistic Turing machine. And then yeah, the reason we allow this kind of probabilistic Turing machine compared to the deterministic Turing machine is that at some point people believe that the probabilistic Turing machine might be able to solve more problem efficiently compared to the deterministic Turing machine, but it actually is not the case. But yes, still to maintain the generality of the thesis, yeah, this extended Church-Turing thesis is described that the probabilistic Turing machine can efficiently simulate any realistic model of computation. And then what do we mean by efficiency? Efficiently. And then efficiently means that if to to simulate another machine, then there might be some kind of overhead. But the increase of overhead is not exponential if the size of the yeah. So let's say that um, you have machine A and machine B, and then to solve the same problem, machine A might take just n to the p, and then motion B might take another n to the p, but with the different amount of time multiplication coefficient like 2. And then in this case, we can say that the B can efficiently simulate a computation model A. However, if it takes like um, 2 to the n to simulate A machine using B machine, then the B machine cannot efficiently simulate A. So that's what we mean by efficiently. And then in this case, we also define that the BPP class, and then BPP means that bounded error probabilistic polynomial time. And then in this case, the class, this class implies that the class of decision problems solvable by a probabilistic Turing machine in a polynomial time, but with the error probability of 1/3 for all instances. And then the extension of this BPP is BQP, and in this case, this probabilistic part is replaced by the quantum part, quantum keyword. And then the definition of the class is very similar. So class of decision problems solvable by a quantum computer in a polynomial time with an error probability of at most 1/3 for all instances, and then that is called as this BQP. So in other words, BQP, the problem belonging to BQP is that most of those problems, such as the factoring algorithm or Schur's algorithm, and then in that case, those problems can be efficiently solved within the polynomial time. So yeah, what people believe who support the quantum computing is that this thesis is not enough. And then what we have to do is we have to change or correct this thesis such that and then this new thesis is called as the quantum complexity theoretical Church-Turing thesis. And then in this case, instead of using the considering the probability, instead of limiting only to the probabilistic Turing machine, we should consider the quantum Turing machine, and then quantum Turing machine can efficiently simulate any realistic model of the computation. So in other words, um, if you can think of, if human can think of any kind of computation model, then and then in principle, quantum Turing machine can simulate or do the calculate the same thing, or solve the same problem with the um, 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 with only the polynomial overhead compared to that new machine. So if this is the first time you see this Church-Turing thesis, then probably this is a little bit confusing. And then I just recommend that you should actually read more chapters about the Church-Turing thesis. So I will stop the today's lecture here, and then from the next lecture, I will get back to the quantum system, and then we will discuss more about some quantum mechanical information property.